Welcome back to the deep dive. Usually when we sit down to talk about cybersecurity, the mental image is pretty standard.
Server rooms, right?
Yeah, server rooms, cloud databases, maybe someone in a hoodie trying to steal credit card numbers. It's all very clean, very digital.
All happening in an office somewhere.
Exactly. But today, we're going somewhere completely different. We are heading to the factory floor.
Oh, it's a totally different beast.
Yeah.
You almost have to unlearn what you think you know about standard IT security.
How so?
We aren't talking about protecting data privacy here. We're talking about protecting physics, kinetic energy, pressure, heat.
Wow. Okay, so this is where digital code meets physical machines. And to guide us through this, we're analyzing the NSE6 OTS AR 7.6 exam.
From the FCSS Secure Networking Track.
Right. And I know exam prep can sound a bit dry, but I want to frame this differently for you listening. The questions in this cert are actually a perfect blueprint for understanding how operational technology or OT security really works.
That is absolutely the right way to frame it. Don't think of it as a test you memorize.
No.
Think of it as a threat model. If the exam writers think you need to know a specific port number or a specific mounting bracket, it's because getting that detail wrong in the real world has massive consequences.
So our mission today is to unpack the technical nuggets hidden in these questions. We've got about 10 key ones that will be our landmarks. And for anyone tuning in who is prepping for this, here's the quick recon.
Go for it.
It's a 65-minute exam. You're looking at 35 to 40 questions, and they throw both multiple choice and multiple select at you.
It's a tight exam.
Yeah.
65 minutes is not a lot of time to second-guess yourself on protocol numbers or firewall modes.
You need to know it cold.
You really do.
Yeah.
Because in an actual OT incident, you don't have time to Google the manual.
Okay, let's dive into the first big theme then, which I'm calling the blueprint. If you're coming from a standard IT background, you're used to what? Flat networks?
Flat networks, maybe some basic VLANs for HR and sales.
Yeah. But in the industrial world, the network is built like a hierarchy.
You're talking about the Purdue model.
Right. The Purdue Enterprise Reference Architecture, or PERA. It comes up immediately. Question 1 in our stack asks about level 1 of this model. It asks, which level is the primary location for programmable logic controllers that execute local process control?
And this is just,
Yeah.
it's fundamental. If you visualize the Purdue model, it's a pyramid.
Okay.
At the very top, level 4 and 5, that's your corporate IT,
Yeah.
email, ERP systems, all the stuff connected to the internet.
Yeah.
As you go down, you get closer and closer to the physical process.
And the question is about level 1. So the answer is that level 1 is home of the PLC,
Yeah.
the programmable logic controller. But let's not just memorize that. What does that layer actually do?
Okay, think of level 1 as the brain stem of the factory, the reflexes.
Brainstem, I like that.
Level 0, which is right below it, that's your sensors and actuators. The actual valves, pumps, temperature gauges, they feel the world. Level 1 is where the immediate decision happens. A PLC at level 1 reads a sensor from level 0, say, tank pressure is 500 psi, and it immediately executes a logic command, open release valve.
So it's not doing big data analysis or checking with the cloud.
No. It is instantaneous. Stimulus, response. That's why it's called local process control. It's happening right there at the machine.
And from a security perspective.
Well, this is where IT folks often miss the point. They look for servers running Windows or Linux, things they know how to patch. But if an attacker compromises a PLC at level 1, they aren't stealing data.
They're controlling the valve.
They are physically manipulating the valve.
Yeah.
They can cause a tank to rupture or a centrifuge to spin out of control.
That distinction leads us right into the biggest culture clash in this field. We're calling it the golden rule of OT. In IT, we're all about the CIA triad, right? Confidentiality, integrity, availability.
And confidentiality is almost always king.
We encrypt everything. If we get hacked, lock the system down, save the data.
Right. A bank detects a breach, they freeze the accounts. It's annoying for the customer, sure. But the money is safe. The priority is keeping the secret.
But question 2 in our stack flips this completely on its head. It asks, when balancing security needs in an industrial plant, which factor is traditionally prioritized?
And the options are probably things like data confidentiality, system availability.
Exactly. Data confidentiality, system availability, user accountability, or file encryption.
And if you answer confidentiality, you fail the exam.
Yeah.
And honestly, in the real world, if you prioritize confidentiality in a plant, you might get fired.
The answer is system availability. Why? Why is availability so non-negotiable here?
Because of the physics we mentioned earlier.
Huh?
Imagine a steel mill.
Oh.
You have a blast furnace with tons of molten metal. You can't just reboot a blast furnace. If that control system goes offline for even an hour, that metal might harden inside the vessel.
And now you have a multi-million-dollar paperweight.
A paperweight, or worse. The cooling system stops, pressure builds up, and you have an explosion. In IT, we prioritize the secret. In OT, we have to prioritize the process. The plant must keep running.
So every security decision flows from that.
Every single one. You can't deploy a tool that adds latency or risks crashing a PLC. If your firewall adds a 50-millisecond delay to inspect a packet and a robotic arm misses its timing because of it, you've just broken the product.
This context is so crucial for the next theme, the language. These machines are not sending emails. They're speaking these very specific, often very old dialects.
Protocols. Yep. This is where the rubber meets the road. If you don't speak the language, you can't secure the conversation.
We've got 2 questions here. Question 3 asks about a major manufacturer associated with the S7 communication protocol. The answer is Siemens.
Right. So in the OT world, you have these massive ecosystems, walled gardens, really. Siemens is a giant, especially in Europe in manufacturing.
So if I walk into a plant and see Siemens PLCs?
You are almost certainly going to see S7 traffic on the wire.
But why does a security analyst need to know that Siemens equals S7? Can't they just see it all as, traffic?
Not if you want to be effective. It's about context. If you're in a Siemens shop and see S7 traffic, that's normal. But what if you see S7 traffic in a plant that uses exclusively, say, Rockwell automation gear?
Ah, that's a huge red flag.
A massive red flag. It's like hearing someone speaking French in a room where everyone is supposed to be speaking Japanese.
Yeah.
Even if you don't speak French, you know something is out of place.
Got it. Then we have question 4, which flips to the other side of the coin. It asks about Modbus TCP, specifically the standard network port for it.
502.
Port 502, that's the one.
If you work in OT, just burn that number into your brain. Modbus is like the English of the industrial world. It's an open standard. Almost every manufacturer speaks it. It's simple, reliable, and everywhere.
But from a security point of view, isn't Modbus kind of naked?
It is completely naked. It was designed in the late 70s. There is zero encryption. There's no authentication. If I can connect to port 502 on your device, I can tell it what to do. I don't need a password. I just send the command.
That is terrifying. So knowing port 502 is open on your firewall is like leaving the front door unlocked.
It's worse. It's leaving the front door wide open with a sign that says, free control of the factory inside. And that's why the exam tests you on it. You have to know to lock that port down.
Which is a perfect segue into the gear. We know we need to protect these devices, but we also know we can't disrupt the process.
Right. You can't just slap a standard IP firewall in the middle of a production line and hope for the best.
And question 5 introduces a feature that seems built for this exact problem. It asks about a FortiGate firewall in transparent mode.
Ah, yes. This is one of the most important concepts for an OT network architect.
The answer is to filter traffic without requiring any changes to the IP addresses of existing devices. Break that down. Why is changing an IP such a big deal? My laptop's IT changes all the time.
Okay, think about a pharmaceutical line that makes vaccines. That line was installed 10 years ago. It went through a rigorous validation process, maybe by the FDA.
Okay.
Every single sensor, every PLC, every server was tested and certified as a complete package. The code in the PLC is often hard-coded to talk to the IP address of the HMI next to it.
So if I, the security guy, come in and say, hey, I need to re-IP this whole network to put in a firewall.
You break the code, the machine stops working. And significantly, you might trigger a requirement to recertify the entire process.
Which costs millions and takes months.
Exactly. It's a non-starter. The plant manager will throw you out. That's where transparent mode comes in.
Okay, so how does it work?
It lets the FortiGate sit between the PLC and the HMI, like a bump in the wire. But it doesn't act like a router. It doesn't have its own IP on that segment. It works at layer 2. To the machines, it is invisible.
But it's still actively inspecting the traffic.
Oh yeah, it's inspecting everything. Applying IPS signatures, blocking bad commands, stopping exploits. But it does it stealthily. You get modern security without the disruption.
It's like a ghost in the machine.
Precisely.
Now, speaking of the environment, let's talk about the physical reality here. We're not in a nice, cool server room. Question 9 asks about ruggedized FortiGate models and a unique mounting characteristic. The answer is din-in rail mounting.
This might seem trivial if you've never been inside a control cabinet,
Yeah.
but it is absolutely vital for deployment.
So paint the picture for us. Where are we?
You are on the floor of a paper mill, or inside a power substation, or an oil refinery. It is hot, maybe 120 degrees Fahrenheit inside the cabinet. There's dust, vibration from nearby turbines, and you do not have a nice 19-inch server rack.
What do you have?
You have a metal cabinet on the wall, and inside there's a metal strip called a DIN-in rail. All the industrial equipment, power supplies, PLCs, relays, they all just clip right onto this rail. It's the Lego system of the industrial world.
So if I bring a standard firewall,
You have nowhere to put it. You'd be duct taping it to the wall. Ruggedized gear clips right onto that DN rail. It also usually has no fans.
no fans because of the dust.
Dust and failure rates. Fans are the first thing to die in a harsh environment. If the fan dies, the unit overheats. Ruggedized gear dissipates heat passively through the metal casing. It's built to survive where a normal server would fry in a week.
Let's move to our next theme, visibility. The old security saying, you can't protect what you don't know you have, and in OT that problem is huge, right?
It's a massive problem. These networks grow organically over decades. Documentation is lost. Contractors come in, add a switch, and leave. We've found devices in plants that nobody knew existed.
And that's where the gatekeeper comes in. Question 6 introduces Fortinet. It asks for its primary role when a new device connects. The answer, to classify the device type and determine its security profile.
Think of Fortinet as a very strict automated bouncer at the club door. A device plugs into a switch port. Before it can send a single packet to the main network, Fortinet steps in. And it doesn't just check a MAC address. It goes deeper.
What's it looking for?
It profiles the device. It looks at how it handshakes, the protocols it tries to use. It says, okay, based on your behavior, you look like a Siemens PLC. Or you look like a generic security camera. Or you are a Windows laptop.
And based on that ID, it assigns a role.
Correct. If it's a PLC, it automatically puts it on the control VLAN with strict access. If it's a camera, it goes to the video VLAN. If it's an unknown laptop, it might get thrown into a quarantine VLAN where it can't talk to anything.
So it stops someone from just plugging in and scanning the whole factory.
Instantly.
But that's just at the moment of connection. What about ongoing inventory? Question 10 brings in Fortism, which it says helps maintain inventory by automatically discovering and updating the asset database.
This is the difference between a snapshot and a movie. Fortinet handles the entry. Fortisim's watching the room constantly.
And why is that automatic discovery so important? Can't you just use a spreadsheet?
A spreadsheet is dead the moment you save it. You need something that listens. Fortisim analyzes logs and traffic flows. If a device that's been silent for a year suddenly wakes up and starts talking Modbus, Fortisim sees it and updates the inventory.
And it does this passively, right?
Exactly. This is a huge gotcha in OT. In IT, we run active scans, we ping everything. If you ping an old PLC from the 90s too fast or scan its ports, you can overwhelm its tiny network card and crash the unit.
You can brick it.
You brick it. So Fortisim just listens to the chatter without poking the bear. It builds that inventory safely.
Okay, we're heading into the final stretch, and we need to address the elephant in the room. Why are we doing all this? The adversaries here are serious. This is Theme 5, the high stakes.
This is where the exam references the global standard, IEC 62443. This is the Bible for industrial cybersecurity.
And question 7 asks about security level 4, SL4. What does SL4 represent? The answer is protection against intentional violation using sophisticated means with high resources.
That is bureaucratic language for nation-state attackers.
Let's calibrate that. What's SL1 or SL2?
SL1 is protection against, casual or coincidental violation, someone making a mistake. SL2 is a generic hacker with low resources. SL3 might be a hacktivist group, but SL4...
SL4 is different.
SL4 means you assume the attacker has unlimited time, unlimited funding, and deep specific knowledge of your system. They have 0 days.
So if you're running a national power grid, you're designing for SL4.
You absolutely have to. The IEC 62443 standard gives you the framework to build a defense that can withstand that level of attack.
And part of that is being able to prove you're doing it right, the paper trail. Question 8 asks about Fortianalyzer in the OT fabric.
Ah, the historian for security.
The answer says its job is to aggregate logs and generate historical security compliance reports.
You can't log into 500 different devices to look for a needle in a haystack. You need a single pane of glass. If an attacker moves from IT to the DMZ to the level 3 network, different devices see different parts of the attack. Fortianalyzer stitches that whole story together.
And the compliance reports? For the auditors.
That's for the auditors.
Yeah.
When regulators come in to check if you're meeting IEC standards, you can't just say, trust me, we're secure. You generate the report. Here is every failed login. Here is every blocked connection on port 502. It turns data into proof.
Thanks for diving deep with us.
Stay safe out there.
And to our listener, good luck on the exam. We'll see you on the next deep dive.